Good morning, everyone. Today I will present my research titled Deep Learning-Based Analysis for Hypertension Prediction in Elderly Populations. This work focuses on using deep learning to improve healthcare for older adults. Hypertension affects over 60% of people aged 60 and above. It is a key contributor to cardiovascular disease and mortality. However, many elderly patients go undiagnosed due to symptomatic progression and lack of regular checkups. Deep learning, particularly bio-LSTM models, offering a promising solution by analyzing complex temporal health data to predict hypertension risk. This research has three research questions. The first one, how can deep learning models use a variety of static and dynamic factors to predict the risk of hypertension in the elderly population? The second one, in the elderly population, which pre-treatment technology can effectively solve the problems of missing and incomplete data to improve the accuracy of hypertension prediction? The last one, how do bio-LSTM models compare to traditional machine learning algorithms in predicting hypertension risk in older adults? And there are also three research objectives. Objective 1, to develop a bio-LSTM framework for predicting the risk of hypertension onset in the elderly population, to design the validated data imputation method for the health records of the elderly so as to mitigate the impact of missing or incomplete data on the prediction accuracy. And the objective 3, to evaluate the prediction performance of the proposed deep learning model against the traditional machine learning algorithms. As for the significance, socially, the model helps prevent the severe conditions through early detection. Economically, it can reduce long-term treatment costs. Methodologically, it is the first to integrate both static and time series data for the elderly using bio-LSTM. And as for the research scope population, the study will investigate the older adults aged 60 years and over, and will use public available electronic health records datasets. And as for the data, it includes static characteristics and temporal data, and we use the bio-LSTM model. I reviewed 10 major studies. I found that many previous studies had some clear strengths. Most of them made effective use of machine learning models and relied on large-scale national datasets, which added credibility to their results. However, I also noticed several important limitations. Many studies had small sample size or didn't specifically focus on elderly populations. More importantly, they often ignored the temporal nature of hypertension, which is a progressive, time-sensitive condition. I also observed that deep learning models used in some papers lacked interpretability, which makes clinic adoption more difficult. That's why I believe there's a strong need for a prediction framework that is elderly-specific, time-aware, and based on robust data sets. This is exactly what my study is aiming to address. So my study focused on 4 key gaps. The first one focused specifically on older adults. Second one used bio-LSTM to model time-based health dynamics. Third one combines static and time series data. The last one applies advanced imputation with MICE and KNN to preserve data quality. As for the research methodology, we have 3 phases. The first one, data acquisition and pre-processing, and the dataset we use trials and research sample older adults from the child's dataset across all available waves. And we used stratified sampling based on the target label to address class imbalance. As for the missing data handling, we use MICE and KNN. MICE is applied to static features like BMI, and KNN imputation can be applied to time series variables. It's a good combination to handle missing data. And other phases like normalization and standardization. And as for the categorical encoding, One-hot encoding is simple and effective for categorical features with a small number of unique values, and ordinal encoding retains meaningful ordering where applicable, and embedding layers are especially beneficial in deep learning contexts. And sequence structure, data partitioning. The entire dataset will be randomly divided into 3 parts: training set, and validation set, and test set. My model uses BIA-LSTM with 64 units, followed by dropout and a dense mode output. It learns by reactional temporal patterns. Training was optimized with Adam and binary cross interrupt. With early stopping for overfitting control, I benchmarked it against logistical regression and random forest models. I evaluated performance using metrics like accuracy, the proportion of correctly predicted instances among all predictions, precision, the proportion of true positives among all predicted positives, recall, the proportion of actual positives correctly identified, FE score, and EUC confusion metrics. My model outperformed the traditional methods and was statistically validated using paired t-tests. RC and PR curves confirmed its strong predictive ability. Contributions and impacts. Academically, this study introduced a new elderly-focused BIA-LSTM framework. Technologically, it demonstrates the power of integrated static and sequential data. Practically, it offers a tool for early intervention and can be embedded into clinical decision support systems. Hypertension is a major health threat for the elderly, but early prediction can significantly reduce its risks and costs. This study introduces a BIA-LSTM-based framework that effectively combines static and temporal health data to predict hypertension risk. The research demonstrates the feasibility of applying deep learning in elderly care through a structured end-to-end approach. Compared to traditional models, the BIA-LSTM shows superior performance in handling complex, time-sensitive health data, offering value for both academic study and real-world health monitoring systems. Thank you for listening.